Welcome to Lesson 15, Laplace Transforms. The definition of the Laplace transform, some of its properties, and its use in solving initial value problems. I am Ronald Johns. Let's consider the definition of the Laplace transform. Let's let little f of t be a function. Its Laplace transform, capital F of s, is defined to be capital F of s is the Laplace transform of little f of t, and it's given by this integral. The integral from 0 to infinity, e to the minus st, f of t dt. Notice that we're integrating with respect to t here, so this integral, its value depends on what s is, and that's why this Laplace transform is a function of s. So we've seen that we're integrating for t going from 0 to infinity. The result is a function of s. Also, we know that improper integrals, this one going from 0 to infinity, for instance, may converge or diverge. This integral may converge for some values of s, it may diverge for some other values of s. So capital F of s is defined only for those values of s for which this improper integral converges. What we'll find out as we go along is that by using the Laplace transform, we can transform transform an initial value problem involving, say, a differential equation plus some initial conditions into an algebraic equation. That algebraic equation will involve capital F of s. If we can find the capital F of s associated with the initial value problem by using algebra, then by using an inverse Laplace transform, we will be able to find out what f of t is. So that will happen in this lecture as we proceed. Let's look at an example. Let's let f of t equal 1 for all t. Find its Laplace transform, capital F of s. Well, by definition, capital F of s, the Laplace transform of 1, is the integral from 0 to infinity e to the minus st times 1 dt. The function 1 is, by this graph we can see over here, identically equal to 1 for all values of t. So to evaluate this integral, this exponential times 1 is just this exponential. Here we have an improper integral going from 0 to infinity. We'll replace that with an integral going from 0 to m and taking the limit of that as m goes to infinity. Now, an antiderivative of e to the minus st is minus 1 over s e to the minus st. So using the fundamental theorem of calculus, we evaluate this antiderivative at t equals 0 and at m, and then subtract. And once we do that, we'll take the limit as m goes to infinity. So when we substitute m in for the t, we get minus 1 over s e to the minus s times m. When we substitute 0 in for the t, we get minus 1 over s e to the 0, minus a minus 1 over s e to the 0, I should have said, which is plus 1 over s e to the 0. And using the fact that e to the 0 is 1, this term is just 1 over s. The term over here, if s is positive, then e to the minus sm goes to 0 as m goes to infinity. So we're just left in that case with this term, which is 1 over s. So what we saw is this calculation holds only if s is greater than 0, because that's when this first term will go to 0. Otherwise, this integral diverges. So what we have then is the Laplace transform, capital F of s, is equal to 1 over s for s greater than 0. Here's another example. Let's let f of t equal e to the at for all t. Let's find its Laplace transform, capital F of s. So capital F of s is the Laplace transform of e to the at, and by definition, this is going to be the integral from 0 to infinity e to the minus st times this function e to the at dt. By laws of exponents, we can combine these two factors into e to the minus the quantity s minus a times t, and that's integrated from 0 to m with respect to t. And since this is an improper integral, we'll take the limit as m goes to infinity of the integral from 0 to m of this stuff. Now, an antiderivative of this integrand is minus 1 over s minus a e to the minus the quantity s minus a times t. Using the fundamental theorem of calculus, then, to figure out the value of this integral, we'll evaluate this antiderivative at m, t equals m, and at t equals 0, and then subtract. And since we're going to look eventually at this improper integral, we want to take the limit as m goes to infinity here also. This stuff right here, by the fundamental theorem of calculus, is equal to this integral from 0 to m, and the limit just carries from one line to the next. Okay, so now substituting m for t and 0 for t and subtracting, we get the limit as capital M goes to infinity, minus 1 over s minus a e to the minus s minus a times m, plus 1 over s minus a times e to the 0. Now 1 over s minus a e to the 0 is just 1 over s minus a, recognizing that e to the 0 equals 1. And if s minus a is a positive number, then minus s minus a will be a negative number, and as m goes to infinity, this will go to 0. So this calculation gives us that this limit is 0 plus 1 over s minus a, only if s is greater than a. In the other cases, this integral that we have up here will diverge. So our result is that capital F of s is equal to 1 over s minus a for s greater than a. Let's look at an example of trying to find the Laplace transform of a function that grows big very quickly. Let's let f of t be e to the t squared for all t. Let's try to find its Laplace transform, which we'll call f of s. Okay, well, capital F of s in this case, the Laplace transform of e to the t squared, is the integral from 0 to infinity e to the minus st times this function e to the t squared dt. Now, this is an improper integral, so we will change it to an integral going from 0 to m and take the limit of that as m goes to infinity. The product of these two exponentials is e to the t squared minus st, integrating that with respect to t going from 0 to m. Now, if we look at this exponent for a minute, no matter what the value of s is here, the value of t squared minus s times t goes to infinity as s goes to infinity. Here's an example. Suppose I let s be 4 for a second. Look at the graph of t squared minus 4t. It looks like this, and as t gets larger and larger and larger, this curve keeps going up. If you look at e to the t squared minus 4t, what's going to happen there? It's shown in red. Well, for negative values of t, e to that negative value is pretty close to 0, but once t squared minus 4t starts getting big out here, e to the t squared minus 4t gets very big and just keeps going up as you increase the values of t. So the integrand grows without upper bound as t goes to infinity, And so it's easy to see that this integral diverges for all values of s. In other words, the Laplace transform capital F of s is undefined for all values of s. Well, why did this happen? And what kind of functions do we think might have Laplace transforms? Well, they can't grow too fast, like e to the t squared. So we can conclude the following. For a function f of t to have a Laplace transform, it must not grow too fast as t goes to infinity. If f of t grows more slowly than e to the at for some positive a, then that function will have a Laplace transform, at least for values of s greater than a. F of s in that case will exist at least for values of s greater than a. It turns out that one big class of functions that do have Laplace transforms are those functions that are of exponential order. Let's talk about what that means. A function f of t defined on 0 to infinity is of exponential order if there exists a positive number a positive number c, and a positive number capital T satisfying the following. The absolute value of f of little t is less than or equal to a e to the ct for all lowercase t's greater than this number uppercase T. Here's a picture. Suppose that this is the curve absolute value of f of t. The horizontal axis is the t-axis. Suppose that we can find an exponential curve ae to the ct and a number capital T somewhere out here, such that once we look at values of little t to the right of this number capital T, this graph is below this graph here, or below, or at least not getting above that curve. It could touch this exponential curve, that's okay. So basically what we're saying here is that as t goes to infinity, this function f of t in absolute value is bounded by an exponential function. So functions of exponential order do not grow too fast. And here's a fact that we should remember. A piecewise continuous function of exponential order has a Laplace transform capital F of s for all s greater than c. Now, this doesn't say that it fails to have a Laplace transform for s less than c. That c was just some number that makes this inequality true for all little lowercase t greater than or equal to that bound capital T. So what we're saying here is this situation guarantees us that for at least all s greater than c, capital F of s will be defined. The Laplace transform will exist for s greater than c. So here's a table of some commonly used Laplace transforms. If the function lowercase f of t is 1, its Laplace transform is 1 over s. The Laplace transform of t is 1 over s squared. The Laplace transform of t squared is 2 over s cubed. The Laplace transform of t to the n, where n is a positive integer, is n factorial over s to the n plus 1. The Laplace transform of sine of at is a over a squared plus s squared. The Laplace transform of cosine of at is s over a squared plus s squared. And the Laplace transform of e to the at is minus 1 over a minus s. This fraction could be written as 1 over s minus a, taking account of this minus sign by multiplying this denominator by minus 1. So also 1 over s minus a for this Laplace transform. Let's talk about the inverse Laplace transform. We earlier saw that the Laplace transform of 1, the function that's constantly 1, is 1 over s. The Laplace transform of 1 is 1 over s. Well, in that case, we can say that the inverse Laplace transform of 1 over s is 1. So Laplace transform of 1 equaling 1 over s implies the inverse Laplace transform of 1 over s equals 1. So the inverse Laplace transform kind of goes backwards from the Laplace transform. If the Laplace transform of little f of t is capital F of s, then the inverse Laplace transform of capital F of s is little f of t. So one question that we would have to ask is, are inverse Laplace transforms unique? And they are almost. The answer to this question is the following. If the Laplace transform of f1 of t is capital F of s, and also the Laplace transform of f sub 2 of t is also capital F of s, the same capital F of s function, then those functions lowercase f1 and lowercase f2 have to be equal for every value of t where both are continuous, where both f1 and f2 are continuous. So if they have the same Laplace transform, these two functions, f1 and f2, can only differ at points of discontinuity. That does not seem surprising because changing the value of an integral at 1 or 2 or a finite number of points doesn't change the value of the integral of that function. Let's discuss the linearity properties of the Laplace transform and the inverse Laplace transform. First, let's look at the Laplace transform. The Laplace transform is a linear transformation. Whenever the Laplace transform of f of t and the Laplace transform of g of t exist, then the Laplace transform of f of t plus g of t equals the Laplace transform of f of t plus the Laplace transform of g of t. The proof is fairly simple. The Laplace transform of f of t plus g of t, by definition, is the integral from 0 to infinity e to the minus st times the quantity f of t plus g of t dt. We can break this integral up into the sum of two integrals, the integral of e to the minus st f of t dt plus the integral of e to the minus st times g of t dt. This first integral is the Laplace transform of f of t. The second integral is the Laplace transform of g of t. The second property that a linear transformation has to have is the following. Laplace transform of a constant times f of t equals that constant times the Laplace transform of f of t. And this would hold for any constant a. The proof of this is omitted. If you write this Laplace transform as an integral, you'll see that it easily follows, just as easy as this proof up here. Also, it turns out the inverse Laplace transform is a linear transformation. The inverse Laplace transform of f of s plus g of s equals the inverse Laplace transform of f of s plus the inverse Laplace transform of g of s. And also, the inverse Laplace transform of a times f of s is equal to a times the inverse Laplace transform of f of s. So both the Laplace transform and the inverse Laplace transform are linear transformations. Let's see how we can use SageMath to find Laplace transforms of functions of t and inverse Laplace transforms of functions of s. In this first cell, we will declare some variables. A, B, C, X, Y, Z, S, T, U, V, N, and I are declared to be variables with the names A, B, C, X, Y, Z, S, T, U, V, N, and I. We'll assume that n is greater than 0. We'll also assume that n is an integer. So let's run this cell. And now let's find the Laplace transform of e to the 3 times t. This is a function of t, and we want our Laplace transform of it to be written as a function of s. Using t for our functions that we're finding Laplace transforms of, and using s as the variable for the inverse Laplace transform is widely used, but this software is fairly flexible and you can use other variable names if you want to. So let's run this one. So the Laplace transform of e to the 3t is 1 over s minus 3. Let's look at this next one, which looks kind of the same, but a little bit of a difference. Laplace of e to the 3 times t. Oh, and I should put in here that this is a function of t, and we want the Laplace transform to be a function of s. So let's run this one. And we get something that was kind of unexpected, perhaps. It isn't 1 over s minus 3. We got e cubed over s squared. What's happening? Well, look at the order of precedence of operations up here. Let's consider that. We have a raising to a power and a multiplication. So raising to a power comes first. So we have the constant e cubed, and that's multiplied by t. So what we have down here is that constant factor, e cubed, and then the Laplace transform of t is 1 over s squared. So we get e cubed times 1 over s squared. If we really want e raised to the quantity 3 times t, we need these parentheses around 3 times t. This is not interpreted in most computer languages the same as what is up here. We have to be somewhat careful. Okay, so now let's go down here, and we have the inverse Laplace transform of 6 over s to the 4th. And let's see what happens with this. This capital F of s function basically is a function of s. We want the inverse Laplace transform to be a function of t. So let's run that one, and we get t cubed. Okay. So now let's try something different. Let's try to make up a short table of Laplace transforms of some commonly used types of functions. So I'm going to make a list. The list is going to be called L, and I'm assigning to this list this stuff right here. The square bracket on the left and the square bracket on the right tell us that this is a list. The 0th element of this list is 1. Then the list, the one element is t, the next one's t squared, and so forth. So first of all, before we do anything else, Let's investigate this list just a little bit further in this statement. But first I better execute this statement assigning things to L. So I'm going to run that first. That's done. And so now we're down here. For I in range 7, print I, comma, a whole lot of blanks, and then there should be a comma here too. And then L sub I. So let's run that and see what happens. So here's what happens. When I is 0, L sub I, L of 0 is 1, which is what we have right here. When I is 1, we're going to print 1 and L sub 1. L sub 1 is the second element in this list L. The indexing of this list L starts with 0. And so the Laplace transform of T, L of 1 is T, L of 2 is T squared, L of 3, L of 4, L of 5, and L of 6. L of 6 is this one, e to the a times t power. So this list is indexed with the index starting at 0 and increasing to 1, 2, 3, 4, 5, and 6. So when we say that I comes from range of 7, that's saying that I has to be in this loop 0, 1, 2, 3, 4, 5, and 6. So here we just printed out the functions. Now the next cell is going to be very similar to this one, except instead of printing out I and L of I, we are going to print the function L of I from that list and the Laplace transform of L of I. That function is a function of t. The transform is going to be a function of s. Let's run that command. And so the Laplace transform of 1 is 1 over s. Laplace transform of t is 1 over s to the minus 2, same as 1 over s squared. Laplace transform of t squared is 2 over s cubed. The Laplace transform of t to the n is s raised to the minus n minus 1 power times gamma of n minus 1. And I will mention that gamma of n minus 1, gamma of n plus 1 is the same as n factorial. So this whole thing could be written as 1 over 1 over s to the n plus 1 power times n factorial. And that could be written then as n factorial divided by s to the n plus 1. We will see that in our table of Laplace transforms shortly. Going on, the Laplace transform of sine of a times t is a over a squared plus s squared. The Laplace transform of cosine of a times t is s over a squared plus s squared. Notice that the numerators are different here for the Laplace transforms of sine and cosine. They have the same denominators, however. The Laplace transform of e raised to the a times t is minus 1 divided by the quantity a minus s. Once again, many of us would simplify this fraction to 1 over s minus a. Now, gamma is defined for non-integers along with integers. And I was surprised when we ran that because I was expecting an n factorial here instead of gamma of n plus 1. So I'm going to check to make sure that n is an integer. I'm going to run this statement, n dot is underlined integer, parentheses because it's a function call, and it comes back and says true. Okay, so for some reason this was not simplified as humans would expect it to be simplified for the formula for the Laplace transform of t to the n. Here's something that we really don't need right now, but I'm just going to mention it. Sometimes we want to simplify these sorts of things to regular math notation. And LaTeX is a mathematics typesetting system that allows you to write formulas and equations at your computer keyboard and have them appear in a LaTeX document looking like standard math. This is going to allow that to happen where we could just cut and paste into software that supports LaTeX. So I'm going to, once again, for I goes from 1, for I in range 7, print LaTeX of L of I, the Lth function that we had up here, the ith function that we had up here in the list L, and also its Laplace down here, and also the LaTeX version of the Laplace transform of L of I, changing from a function of t to a function of s. So we'll execute this one, run it, and for those that have used LaTeX before for maybe writing mathematics research papers or capstone papers for many senior math majors, this will write things using LaTeX, which can be then easily converted with proper programs to what look like mathematical objects that we usually write by hand. The Laplace transform of the derivative of a function of t and the Laplace transform of the second derivative of a function of t have some interesting formulas that can help us solve differential equations and initial value problems. We'll find out that these will simplify initial value problems into algebraic equations. So first property, if f is continuous, piecewise smooth, and of exponential order. Exponential order, remember, means that f of t in absolute value is less than or equal to a e to the ct for all t greater than or equal to some number m. Then the Laplace transform of f prime of t turns out to be the following: s times capital F of s minus little f of 0, and this holds for all s greater than c, the c that was up here. Now, capital F of s right here is the Laplace transform of little f of t. So this tells us that the Laplace transform of f prime of t can be written in terms of the Laplace transform of f of t. If we use this formula twice, once for f and once for f prime, we can get this following formula. The Laplace transform of the second derivative of f at t is equal to s squared capital F of s minus s little f of 0 minus f prime of 0. Okay, so this formula up here for the Laplace transform of f prime of t has two terms. The Laplace transform of f double prime of t formula down here has three terms. And we notice in this formula that the powers of s from left to right decrease. S squared, s to the first, s to the 0. As far as our little f function, the order of the derivatives increases. F of 0 here, f prime of 0 here. The 0th derivative, the first derivative. So the powers of s decline, the order of the derivatives increases. These two formulas will allow us to turn initial value problems at least second order initial value problems into algebraic problems. There are formulas similar to this for the Laplace transform of the third derivative, fourth derivative, and so on. You can find that easily in reference material differential equation textbooks and also on sites on the internet. If you Google Laplace transform of derivatives, you'll probably find many sites that will tell you what the generalizations of these two formulas are. So let's show why the formula for the first derivative holds. Laplace transform of f prime of t equals s capital F of s minus little f of 0. Okay, well, let's start with the Laplace transform of f prime of t, and let's just use the definition of the Laplace transform. So it's equal to the integral from 0 to infinity e to the minus st times this function f prime of t dt. Now we're going to make a substitution. We'll let u be e to the minus st, so du will be minus s e to the minus st dt. We'll let dv equal f prime of t dt, so integrating this, v is just f of t. So what we're going to do with the substitution is use integration by parts. Well, before we do that, first we'll just take care of this indefinite integral. The integral from 0 to infinity of this stuff is the limit as t goes to infinity, the integral from 0 to t of that same stuff. Okay, so now let's look at what we have down here. We still have this limit, and now what we're looking at here is the integral from 0 to t of u times dv. And so that's equal, by integration by parts, to u times v minus the integral of v du. So first of all, u times v is going to be e to the minus st times f of t. That's what we have here. And for this definite integral, will be looking at that from 0 to t, plugging in t into here, plugging in 0 into here, and subtracting. Okay, we also have minus the integral of v du. Okay, so v is f of t, and du up here is minus s e to the minus st dt. So minus v du, minus a minus is going to give us a plus here. The integral from 0 to t, s e to the minus st from this, f of t dt. Okay, and now let's plug in t, capital T, for the lowercase t here. Plug in 0 for the lowercase t here. We get this term, plus we get this integral, and we still have the limit as t goes to infinity, capital T goes to infinity outside. Now, this term in the limit is going to go to 0. How can we see that? Well, e to the minus st capital F of t is less than or equal to e to the minus s capital T times a e to the ct, because f is of exponential order. And now these can be combined into a times e to the minus s minus ct, and as long as s is greater than c, this thing will go to 0, because we'll have e to a negative positive number times something that goes to infinity. So this exponent goes to minus infinity, e to that exponent goes to 0. And so what we're left with is what? The limit of this first term is 0. We're left with this term, e to the 0 is 1 times f of 0 is just f of 0. And we're also left with the limit of this integral from 0 to t. And if we look at that carefully, we'll notice once we pull out this factor of s, the rest of this is just a Laplace transform. So the limit of this stuff right here is just going to be s times the integral from 0 to infinity e to the minus st f of t dt. And then this term is s times the Laplace transform of f of t. And this term right here gives us this minus 0. This can be simplified a little bit further into s capital F of s minus f of 0. And so we've shown that the Laplace transform of f prime of t, if we have f being of exponential order, is equal to s capital F of s minus little f of 0. Shortly, we're going to use the Laplace transform to solve some initial value problems, differential equations plus initial conditions. In order to do that, I'm going to change the notation that we use just a little bit. Suppose we have a differential equation involving the function y of x. Then we'll use this notation. The Laplace transform of y of x we'll call capital Y of s. So it's going to be the integral from 0 to infinity e to the minus sx times y of x dx. If we have a differential equation involving x of t, then we'll use the notation capital X of s is going to be the Laplace transform of x of t, which is the integral from 0 to infinity e to the minus st times x of t, and this should be dt. So here is going to be our overall scheme for solving an initial value problem. We start with an initial value problem involving y of x, and we apply the Laplace transform to that, and we will get an algebraic equation involving y of s. Then what we'll do, since this is just an algebraic equation, is use some high school algebra, or perhaps junior high school algebra, to solve for y of s, the Laplace transform of y of x over here. Once we find what y of s is, capital Y of s is, we will apply the inverse Laplace transform to this to find the solution to our initial value problem, little y of x. So we take a differential equation plus initial conditions, change it into an algebraic equation, solve the algebraic equation, and then apply the inverse Laplace transform to get the solution to this initial value problem up here. As an example of using the Laplace transform to solve an initial value problem, let's consider the following. The second derivative of y with respect to x plus the derivative of y with respect to x minus 6y equals e to the minus x. Initial conditions, y of 0 equals 2, y prime of 0 equals 3. We'll take the Laplace transform of both sides of this equation up here. The Laplace transform of the left-hand side equals the Laplace transform of the right-hand side. Now, how do we find the Laplace transform of e to the minus x? If we look in tables of the Laplace transform, they are available in books and also on the internet, we'll find that the Laplace transform of e to the ax is 1 over s minus a. So, let's see what happens then. The Laplace transform of e to the minus x is going to be 1 over s minus a minus 1, which is 1 over s plus 1. So that takes care of the right-hand side. What about the left-hand side? The Laplace transform of this second derivative of y with respect to x is s squared capital Y of s minus s little y of 0 minus little y prime of 0, plus the Laplace transform of the derivative of y with respect to x is s y of s minus little y of 0. The Laplace transform of minus 6y is minus 6y of s. And we already saw that the right-hand side becomes 1 over s plus 1. Okay, so now what we need to do is plug in the value of y of 0 wherever it appears up here, and also plug in the value of y prime of 0, which happened to be 3. So when we do that, we get from here s squared y of s minus 2 times s minus 3. And then from here, we get sy of s minus 2, then minus 6y of s equals 1 over s plus 1. Okay, this is an algebraic equation for y of s, the Laplace transform of the solution to our initial value problem. So let's find y of s using a little bit of algebra. First of all, collecting the y of s terms, which are here, here, and here, we get s squared plus s minus 6 times y of s, and that has to equal 1 over s plus 1 plus 2s, and here we have a minus 3 and a minus 2, which add up to a minus 5, so when we add it to both sides, we get a plus 5. So this times y of s equals this stuff. To solve for y of s, let's just divide both sides of the equation by this factor s squared plus s minus 6. So y of s is 1 over s plus 1 times s squared plus s minus 6. That's the first fraction. And then the second fraction is 2s plus 5 over that s squared plus s minus 6. Okay? And now, s squared plus s minus 6 factors into s minus 2 times s plus 3, which is what we have here. This first fraction remained unchanged from one line to the next. Now, what we're going to have to do is to find the inverse Laplace transform of this thing. And you're not going to find formulas for inverse Laplace transforms of fraction as complicated as this. What we'll have to do is write this as a sum of partial fractions, and maybe do it to this also, and then find the inverse Laplace transform. So far, we have that capital Y of s is equal to 1 over s plus 1 times s minus 2 times s plus 3 plus 2s plus 5 over s minus 2 times s plus 3. That basically is from the last transparency and factoring a quadratic that appeared there. So now, by partial fractions, this fraction here should equal a over s minus 2 plus b over s plus 1 plus c over s plus 3, where a, b, and c are constants to be determined. So what we need to do to find a, b, and c is to put this stuff over a common denominator, which happens to be the product of these three factors in the denominators, which happens to be the same as the denominator over here. So let's multiply this first fraction by s plus 1 times s plus 3 in both numerator and denominator, and do similarly for these two fractions. And so what we get then is a times s plus 1 times s plus 3 over that denominator, plus b times s minus 2 times s plus 3 over that denominator, plus c times s plus 1 times s minus 2 over that denominator. So now let's multiply these numerators out and collect like powers of s. If we do that, we have s squared times the quantity a plus b plus c plus s times 4a plus b minus c plus a constant term, 3a minus 6b minus 2c, over that common denominator. So now we compare that to the original fraction that we have up here. This stuff just has to be 1 over that denominator. 1 over this denominator. So that means the coefficient of s squared has to be 0. The coefficient of s has to be 0. The constant term here has to equal 1, this numerator that we have here. Okay, so we need to solve these three equations and three unknowns, and hopefully you've seen solutions of systems of linear equations before. There are many methods to do it. We could start by writing the augmented matrix for this system of equations. We'll just write down the coefficients of a, b, c, and the constant terms. So this first equation in the matrix corresponds to the row 1, 1, 1, 0. This second equation responds to 4, 1, minus 1, 0. This third equation corresponds to 3, minus 6, minus 2, 1. Now, if we reduce this matrix to reduced row echelon form, and we can do it easily these days on calculators. The TI-84, TI-85, TI-86 all have matrix operations built in, and you can just type this matrix into the editor and then reduce it. And when you do, you'll get this matrix. This is a matrix corresponding to an equivalent system of equations, same solution set as the system that we started with. But if we look at this, this basically says 1a plus 0b plus 0c equals 1/15. That means that a has to equal 1/15. The second equation in this equivalent system, 0a plus 1b plus 0c equals minus 1/6, tells us that b is minus 1/6. The third equation, 0a plus 0b plus 1 times c equals 1/10, tells us that c is 1/10. So coming back to here, we now know what a, b, and c are. We can substitute those in, and we have that 1 over this denominator is 1/15 over s minus 2 plus minus 1/6 over s plus 1 plus 1/10 over s plus 3. Now, that takes care of simplifying this first term by partial fractions. We can also simplify this second term by using partial fractions, and if you do it, you will find out that 2s plus 5 over s minus 2 times s plus 3 is equal to 9/5 times 1 over s minus 2 plus 1/5 times 1 over s plus 3. So far, we have capital Y of s was equal to the sum of these two fractions. We used partial fractions and decomposed this first fraction into the sum of these three fractions. This second fraction by partial fractions is equal to these two terms. So notice that some of these terms have the same denominator. Here we have 1/15 times 1 over s minus 2. Over here we have 9/5 times 1 over s minus 2. If you add those terms together, you'll have 28/15 times 1 over s minus 2. The rest of the terms simplify to minus 1/6 times 1 over s plus 1 plus 3/10 times 1 over s plus 3. Okay, so that's capital Y of s, the Laplace transform of our solution to the initial value problem. So to find the solution to the initial value problem, little y of x, we just take the inverse Laplace transform of this stuff, which is what we have right here. Now, let's remember that the Laplace transform of e to the ax is 1 over s minus a. So from that, we get the formula, the inverse Laplace transform of 1 over s minus a is e to the ax. Okay, so let's look at this then. The inverse Laplace transform of 28/15 times 1 over s minus 2 is just 28/15 times e to the 2x. The inverse Laplace transform of minus 1/6 times 1 over s plus 1 is just minus 1/6 times e to the minus x. The inverse Laplace transform of 3/10 times 1 over s plus 3 is just 3/10 times e to the minus 3x. And so this is the solution to the initial value problem that we considered earlier. Let's look at another example. Let's solve the second derivative of x with respect to t plus 9x equals 50e to the minus t. Initial conditions, x of 0 equals 7, x prime of 0 equals minus 5. We'll solve this by using a Laplace transform applied to the function x of t. So the Laplace transform of the left-hand side of this equation equals the Laplace transform of the right-hand side of that equation. Now, looking at the left-hand side, the Laplace transform of the second derivative of x with respect to t is s squared capital X of s minus s little x of 0 minus x prime of 0. The Laplace transform of 9x is 9 times capital X of s. The Laplace transform of 50e to the minus t is 50 over s plus 1. So here we have an equation. The values of x of 0 and x prime of 0 we are given up here as initial conditions. So we'll plug them in. Minus s x of 0 is minus 7 times s. Minus x prime of 0 is going to be minus a minus 5, which is plus 5. So this part here simplifies to this part right here. We also have a plus 9x of s plus 9x of s here. The right-hand side we've already talked about. Okay, well, let's collect like powers of s again. We can write this equation as s squared plus 9 times x of s. Okay, now where did that come from? We have s squared x of s plus 9 x of s. So these two terms give us this. We also, then on the other side, we have 50 over s plus 1. I'll subtract 5 from both sides of the equation, and I'll add 7s to both sides of the equation. So we've almost solved for x of s here, but not quite. We have to divide both sides by s squared plus 9. So x of s is this term divided by s squared plus 9 plus this term divided by s squared plus 9. Okay, and now when we look at this, what we notice is that in the denominator, in this fraction and in this other fraction, we have an irreducible quadratic factor. And what we saw before with partial fractions is that we handle these irreducible quadratic factors in the denominator slightly differently than we would just distinct linear factors. So we'll have to see how to handle that. Continuing our solution, so far we found that x of s, the Laplace transform of little x of t, is 50 over this denominator plus this fraction also. If we look at this first fraction, the denominator factors into a linear factor times an irreducible quadratic factor. That means that we can expand this fraction using the method of partial fractions into the sum of simpler fractions. And so that's what we'll look at next. We're just going to consider this part first. 50 over that denominator is going to be a constant a over s plus 1 plus a constant b times s plus c over s squared plus 9. Now, a, b, and c are not arbitrary constants. We have to find their values that this function of s is identical to this function of s. So this equation here contains enough information for us to compute a, b, and c. To do it, we will first combine these two fractions together over a common denominator. And what we get in that case is the following. By multiplying this fraction, numerator and denominator, by s squared plus 9, and multiplying both numerator and denominator of this second fraction by s plus 1, we will get a common denominator. And then adding these two over that common denominator gives us the following. A times s squared plus 9 plus bs plus c times s plus 1 over that common denominator. Now, if we simplify this by combining like powers of s, we have an a times s squared here, we have a bs times s here. Those add up to the quantity a plus b times s squared. Where do the s terms come from? We have bs times 1 plus c times s. Those combine to give the quantity b plus c times s. And the constant term is going to be what? We have a times 9 here and c times 1 here, which results in 9a plus c. So this fraction can be rewritten this way. These two functions of s have to be identical. That means, since they have the same denominator, these numerators must be equal. So this stuff up here must equal the constant 50. So this numerator must be 0s squared plus 0 times s plus 50. So that tells us then that a plus b has to be 0, b plus c has to be 0, and 9a plus c has to be 50. Solve these simultaneous linear equations by any method that you want, and we will find that a equals 5, b equals minus 5, and c equals 5. So at this stage, we can plug those a, b, and c values back here to get a representation of this first fraction that we were looking at. So 50 over s plus 1 s squared plus 9 is 5 over s plus 1 plus, looking up here, minus 5s plus 5 over s squared plus 9. Now, x of s was this fraction which we just decomposed, plus this other fraction. So at this stage, we can say that x of s is these two fractions plus this last fraction. Now, this can be simplified somewhat. This fraction and this fraction have the same denominator, so we can easily add these two fractions together. Minus 5s plus 7s is 2s. Minus 5 minus 5 is 0. And so these two fractions simplify to this fraction, 2s over s squared plus 9. So capital X of s, the Laplace transform of the solution to our initial value problem, equals this, the sum of these two fractions. So if we want to get the solution to the initial value problem, x of t, all we have to do is take inverse Laplace transforms. Remember that the inverse Laplace transform is linear. So the inverse Laplace transform of this stuff is the inverse Laplace transform of this first fraction plus the inverse Laplace transform of the second fraction. So by linearity, the inverse transform of this first fraction is 5 times the inverse Laplace transform of 1 over s plus 1. The inverse Laplace transform of this second fraction is 2 inverse Laplace transform of s over s squared plus 9. Now, we've seen these two types of inverse Laplace transforms before. The inverse Laplace transform of 1 over s plus 1 is just e to the minus t. The inverse Laplace transform of s over s squared plus 9 is going to be cosine of 3t with those coefficients 5 and 2, those constant coefficients in front. So what we have shown is that the solution to our initial value problem is 5 times this inverse Laplace transform plus 2 times this one, which is 5 e to the minus t plus 2 cosine of 3t. So let's solve an initial value problem using Laplace transforms and inverse Laplace transforms. So we're going to look at an example of a system of linear ordinary differential equations. We're going to have, in this case, two differential equations, water flowing from one tank into another. And so here's the setup. We have tank A with some, turns out, salt water in here, and we have a pipe where salt water can flow in. This water is going to be mixed up and then sent through another pipe into tank B, where the mixture here is mixed up also, and until it's basically homogeneous density, and then piped out here. So here's what's going to happen. At time t equals 0, tank A has 1,000 liters of water mixed with 20,000 grams of salt. So that's 20 grams of salt per liter concentration. On the other hand, tank B has 300 liters of water mixed with 10,000 grams of salt. So that turns out to be 33 1/3 grams of salt per liter. So the saltwater concentration in tank B, grams of salt per liter, is higher than the concentration in tank A. So now what happens? Seawater is pumped into tank A at a rate of 50 liters per minute. Seawater has 30 grams of salt, 35 grams of salt per liter. The salt water in A is continuously mixed, and the mixture in A flows into B also at 50 liters per minute. So salt water is entering at 50 liters per minute, and mixture is exiting at 50 liters per minute. So then what happens? Salt water flows out at 50 liters per minute. So over here, also out 50 liters per minute. So 50 liters per minute in, 50 liters per minute out of tank A and into tank B, 50 liters per minute leaving tank B. That means that the level of water and salt is going to remain constant in these tanks. The concentration of salt might not, but the volume of water is not going to change with time. So the question then we're going to answer is how much salt is in tank A at time t and how much is in B. Okay, so we're looking at the amount of salt measured in grams, not concentration. So let's let x sub A of t be the amount of salt grams in tank A at time t, and let x sub B of t be the amount of salt in tank B at time t. So now, we solved previously, in a previous lecture, a problem kind of similar to this, where salt water ran into one tank and out of one tank, and we asked what was going on inside that one tank. But here we have two tanks, tank A and tank B. And so that makes things complicated, a little bit more complicated. Not hard, just more details to take care of, I guess. And so we are keeping track of how much salt is in tank A, measured in grams, and that's x sub A of t. We're also keeping track of how much salt, measured in grams, is in tank B, and that's x sub B of t. So let's look at tank A for a minute. We're going to look at the rate of change of the number of grams of salt in tank A with respect to time t. T in this case is going to be measured in minutes, since our flows over here are in minutes. So we have the concentration of salt in tank A times, okay, let me start over again. We're looking at the rate of change of salt in tank A with respect to time. So salt is entering the tank this way. It's entering at 50 liters per minute, and the salt water has 35 grams of salt per liter. So the amount of salt entering the tank through this pipe, the rate that it enters, is the concentration of seawater salt times the flow rate. Then salt is also leaving tank A, and that amount of salt, the rate that salt leaves the tank, is the concentration of salt in that tank. Well, there are at any time t, there are x sub A of t grams of salt in the tank. There's a volume here of 1,000 liters. So this is the concentration at any time t in the tank, and it's multiplied by the flow rate out of that tank, which is 50. Now, let's make short work of the second equation. We're looking at how the amount of salt in tank B changes. So the rate of change of the amount of salt in tank B is equal to the rate that salt is flowing in, which was just like it was down here, x sub A divided by 1,000 times 50, minus the rate that salt leaves the tank in grams per minute, and that's the concentration of salt in tank B, which is x sub B over 300, times the rate fluid is moving out, which is 50. Okay, now we have a couple initial conditions. At time 0, the amount of salt in tank A is 20,000 grams, And also at time 0, the amount of salt in tank B is 10,000 grams. So here we have a different type of initial value problem than we had before. We have a differential equation involving x sub a of t, and we have a differential equation involving x sub b of t. X sub a and x sub b are both functions of t. They change with respect to time. We have an initial condition to tell us how things are starting in tank A, and also how much salt we have at time 0 in tank B. So this is a little bit different from the last differential equation we considered. Here we have two differential equations, and they're first order differential equations, and we also have initial conditions, one involving x sub a and one involving x sub b. So what do you think should happen here? Well, what did we do when we had a differential equation and an initial condition before? We took Laplace transforms. So what's going to happen here is we'll take a Laplace transform of this equation, a Laplace transform of both sides of this equation, and that will give us some algebraic equations, and maybe not algebraic, but they're not differential equations. And then we'll use these initial conditions to solve for capital X sub a of s, capital X sub b of s, and then we'll take inverse transformations to find the solution to this initial value problem. So that's what we're going to be doing starting on the next slide. So here are the two differential equations and the initial conditions that we saw on the previous slide. So what are we going to do? We'll take the Laplace transform of both sides of this equation. So the Laplace transform of the derivative of x sub a with respect to t equals Laplace transform of this right-hand side, which is right here. The second equation is just taking the Laplace transform of both sides of this equation. The Laplace transform of the derivative of x sub b with respect to t is the Laplace transform of this stuff over here, x sub a over 1,000 times 50 minus x sub b over 300 times 50. Okay, so then let's see what happens. The Laplace transform of this derivative is just going to be s x sub a of s minus x sub a of 0, little x sub a of 0. That was using our formula for the Laplace transform of the first derivative of a function. Then take the Laplace transform of this right-hand side term by term. And so we get 35 for this one, 35 times 50 over s, minus, and then the Laplace transform of this stuff is just 50 over 1,000, which we see right here, times the Laplace transform of x sub a, which is right here, x sub a of s. We do similar things with this second equation. This Laplace transform of a first derivative is x sub b of s minus lowercase x sub b of 0. Remember that these are functions of time, and we're evaluating them at time equals 0 here. The Laplace transform of this stuff on the right-hand side is done exactly as we did earlier for the top equation. The Laplace transform of this term is 50 over 1,000 times capital X sub a of s. The Laplace transform of 50 over 300 times this is minus 50 over 300 capital X sub b of s. Okay, let's look at this equation. We have capital X sub a here, and we have capital X sub A here. And so let's try the following strategy. Let's get the capital X sub A's and X sub B's, wherever they are, on the left-hand side of the equation eventually, and the other stuff on the right-hand side. So we'll do that partly, I guess, on the next slide. But first, let's remember X sub A of 0 is 20,000, X sub B of 0 is 10,000. So we'll just plug those in to these two equations for these two values here. And now let's look at this. I'm going to move this term to the other side, and I'm going to move this term and this term to the other side over here. And we're going to do that in the next slide. Okay, so here are the two equations that we saw on the previous slide. So let's see, what are we going to do? Starting with this equation up here, I'm going to add 50 over 1,000 X sub A of S to both sides of the equation. And I'm also going to add 20,000 to both sides of the equation to move it over here. So we can rewrite this equation as this term, S X sub A of S, plus this term here, 50 over 1,000 X sub A of S, equals this stuff, 20,000, plus this stuff, 35 times 50 over S. Now, let's look at the second equation. Let's subtract this X sub A of S term from both sides of the equation, and let's add 50 over 300 X sub B of S to both sides of the equation, and also let's add 10,000 to both sides of the equation. When we do that, we get S X sub B of S plus 50 over 300 X sub B of S minus 50 over 1,000 X sub A of S. Okay, that takes care of this term, and this term. And then on the other side of the equation, we just have this, 10,000. Okay, so now we look at this, and the first thing we notice is that both of these terms involve X sub B of S. So we can combine these together by adding coefficients. The top equation, we'll just do a little bit of numerical arithmetic type calculations. So let's see, this first equation we can write as S plus 50 over 1,000, that quantity, times X sub A of S. And that becomes S plus 1/20th X sub A of S. 50 over 1,000 is just 1/20th. Okay, plus, okay, there's no X sub B of S term here. So I'm going to include it as 0 times X sub B of S. Then looking at the right-hand side, 20,000, that doesn't need simplification. 35 times 50 over S, that turns out to be 1750 over S. Now, let's move to the second equation. We have a minus 50 over 1,000 X sub A of S. We can write that as minus 1/20th X sub A of S. And we also have two terms involving X sub B of S. We can combine them into this term, the quantity S plus a sixth times X sub B of S. And then on the right-hand side, we have 10,000. Okay, so we have two equations here in capital X sub A of S and capital X sub B of S. And solving these equations is not hard. It's solving two equations and two unknowns, but it does get a bit messy. And the taking inverse Laplace transforms after that involves partial fraction decomposition. We could do all of this by hand, but we've done that sort of stuff by hand earlier. And so we're going to use SageMath to do these computations for us, starting on the next slide. So the system of equations that we need to solve is up here. We're solving for capital X sub A of S and capital X sub B of S. We have two equations in those two unknowns. S plus 1/20th, that quantity, times X sub A of S plus 0 times X sub B of S equals 20,000 plus 1750 over S. Second equation, minus 120 X sub A of S plus S plus 1/6 times X sub B of S equals 10,000. So let's set up those equations to be solved using SageMath. So first we'll declare S to be a variable, and now we'll let A be the coefficient, the augmented matrix for this system of equations up here, this system of linear equations. Something times X sub A plus something times X sub B equals something, something times X sub A plus something times X sub B equals something. So A will be the matrix, and for this first equation we have S plus 50 over 100 for the first coefficient, 0 for the second coefficient, and then on the right hand side 20,000 plus 35 times 50, that's the 1750 we have up here, divided by S. The second row of the matrix corresponds to the second equation. Minus 1/20th is minus 50 over 1,000. The next coefficient, X plus 1/6, I wrote as X plus 50 over 300. And on the right hand side, 10,000. So we'll first, after executing these two cells, we'll execute this third cell, show the matrix A that we just defined up here, and we can see that it is the augmented matrix for this system of equations. Okay, then we'll get this matrix in reduced row echelon form. In reduced row echelon form, we get a matrix corresponding, remember, to an equivalent system of equations, a system of equations that has the same solution as the system of equations that we started with. So this matrix says that 1 times X sub A of S plus 0 times X sub B of S equals this, and the second row gives us 0 times X sub A plus 1 times capital X sub B equals this. So from here we can read off what X sub A is equal to and what capital X sub B is equal to. For the system of equations that we had, two equations and the two unknowns, capital X sub A of S and capital X sub B of S, the reduced row echelon form of the augmented matrix A we saw was this. Got it by using SageMath. So capital X sub A of S is equal to this. Capital X sub B of S, 1 times capital X sub B of S, is equal to this. And so we now know the Laplace transforms of the solution functions, lowercase x sub A of t, x sub B of t. The Laplace transforms of those two are these things. So what we need to do is to get back to the solution to the initial value problem by using the inverse Laplace transform. So we will declare t to be a variable, and then lowercase x sub A of t is the inverse Laplace transform, of this stuff, which is what we have right up here. This is a function of s. We want the inverse Laplace transform to be a function of t, and then we will show x sub a of t. When we execute this cell, we find that x sub a of t is minus 15,000 e to the minus 1/20th times t plus 35,000. Then we'll do something similar for x sub b of t. Capital X sub b of s was this stuff, so lowercase x sub b of t is going to be the inverse Laplace transform of this stuff. 1500 times 7 over s plus 80 divided by 20 times s plus 1, which is what we have here, plus 40, which is what we have here, all divided by 6s plus 1, which is what we have here. This is a function of s. We want the inverse Laplace transform written as a function of t. And then we will print x sub b of t, which turns out, when we execute this cell, to be minus 45,000 divided by 7 times e to the minus 1/20th t plus 41,500 divided by 7 times e to the minus 1/6 t plus 10,500. When we used the show command here, the output was in kind of standard math type. When we just printed x sub b of t, it was a linear display showing the numbers and the operations and the functions that were involved. But in any case, up here we have x sub a of t, and down here we have x sub b of t, which those two functions are the solutions to the amount of salt in tank A and in tank B. Remember, we had salt water in both of those tanks. The amount of salt water at time t, the amount of salt in each of those tanks at time t. So let's graph x sub a of t and x sub b of t. We'll have two plots for the amount of salt in each tank as a function of time. By using the command ga equals plot x sub a of t, t going from 0 to 1,000, and then show or display g of a, the graph. X sub a of t is a graph that looks like this. The amount of salt starts at 20,000 at time 0, and then it increases fairly rapidly and levels off at about, I guess, 35,000 perhaps, something like that. And this is to be expected because as time goes on, the amount of salt in the tank is going to be determined by the concentration of salt water entering the tank. As time goes to infinity, the initial condition kind of washes away in that wash of seawater entering tank A. And so the concentration approaches some limiting constant value. Similarly, for tank B, if we look at the amount of salt in tank B, it started at 10,000 and then at time 0, and then as time went on, first it decreased sharply, and then it started going up again, and eventually leveled off for a more or less constant concentration from that point on. So both of these graphs show the amount of salt in each of those two tanks approaches in the limit some constant value. Here's an expanded time, I guess you can say graph, of x sub e of t. Here t just goes from 0 through 50, whereas on the other graph it went up to about 1,000, I think, on the horizontal axis. So what we can see from here is the amount of salt in the tank, measured in grams, I believe, starts at time 0 at 10,000 grams of salt. Then the amount of salt in grams decreases until it looks like about time t equals 10, and then it starts increasing again. And here, if we went further out, we would see that it eventually levels off. So we saw that at first the amount of salt in tank B decreases and then increases, and we can explain why this happened, because at the beginning the concentration of salt in tank B was greater than that in tank A, and initially the tank A mixture flowing into B diluted the salt concentration in tank B, and so that explains why this is going down here. But afterwards, eventually, the concentration of salt in the seawater that enters tank A and later enters tank B causes the amount of salt to go up again in tank B. So somewhere around t equals 10, it looks like tank B has its minimum amount of total salt in that tank. So let's look at two plots, the plots of the concentrations of salt in tanks A and B, and we're going to put them on one graph over here. So first of all, the concentration of salt in tank A is just the amount of salt in tank A at time t divided by the number of liters of fluid in tank A, and so it's x of A of t divided by 1,000. And so we're going to plot this concentration from t goes from 0 to 1,000, and we'll call that plot Ca. Similarly, we will plot the concentration of salt in tank B. Tank B just has, at any particular moment in time, 300 liters of liquid in it, water, and the amount of salt in that water, measured in grams, is x sub b of t. So this is the concentration. We'll plot that also, t going from 0 to 1,000, and this one will let the color of the graph be red. By default, this first graph will be blue. And then we're going to show as a graph Ca plus Cb. We're going to combine the two plots on one graph. So when we look at this, we see a blue curve that starts down here and goes up, 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 and then levels off over here. The red curve, it's kind of hard to see where it starts, but maybe around in here somewhere, and then it goes down, and then it goes back up, and then it levels off. And as time goes on, the two curves kind of coalesce into what looks like one curve here. You can't really tell them apart because they're so close. And why does that happen? Because at this time down here, 400, 600, and so forth, the concentrations of salt in tanks A and B are nearly identical to that of the concentration of salt that enters from the sea, since we had seawater being pumped into tank A and then pumped into tank B from there. So both of the concentrations approach the same limiting value as t goes to infinity. So here are the main points of this lesson. We define the Laplace transform of a function. The Laplace transform of the function little f of t is the integral from 0 to infinity e to the minus st times f of t dt. This is going to be a function of s, and we often called it capital F of s. If we had lowercase f of t, then we had capital F of s. We discussed the linearity of the Laplace transform. For any constants a and b, we have the following. The Laplace transform of the constant a times f of t plus the constant b times g of t is a times the Laplace transform of f of t plus b times the Laplace transform of g of t. The inverse Laplace transform is also linear. If we had inverse Laplace transforms, it would satisfy a similar equation to what we have up here. We learned how to take the Laplace transforms of derivatives of a function. The Laplace transform of the first derivative of f at t is s capital F of s minus little f of 0. The Laplace transform of the second derivative of f of t is s squared capital F of s minus s lowercase f of 0 minus f prime of 0. These formulas can generalize to find Laplace transforms of third derivatives, fourth derivatives, and so forth. We used these formulas and the linearity property up here to solve initial value problems. We solved an initial value problem by using the Laplace transform to turn that initial value problem into an algebraic problem. We then solved the algebraic problem and then took an inverse Laplace transform of that to find the solution to the initial value problem. We also extended this to see that we could solve a system of two first-order differential equations by using the Laplace transform. The example that we solved used two tanks of water and salt mixtures connected by pipes. We will continue our treatment of the Laplace transform in the following lecture. I hope you continue. Thank you for watching. Have a good day. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.